Hello everyone, and welcome to this video titled Derivatives of Trigonometric Functions. In this video, I'm going to be taking you through a preview version of a Knewton Alta Homework Assignment that's also titled Derivatives of Trigonometric Functions. So please understand that this is going to be a preview version of the assignment and that the questions I go over in this video may not be the exact same questions that you will go over when you work on it on your own, but the objectives are the same, and hopefully the way I go about doing things, should be similar to the way you're doing them and help you get through the assignment when you work on it yourself. Okay, so here we are at Knewton Alta, and you have the preview of, for this particular course, I'm in section 3.5, right, the derivatives of trigonometric functions. Upper right-hand corner, you should see the mastery bar, which tells you how far along you have gotten in the assignment. Next to that, the activity log. You click on that, you can see all the objectives from the assignment. Looks like there's only one section of objectives here called, derivatives of trigonometric functions. And there are 4 objectives. Then you have your current objective, a question related to that current objective. And at the bottom of every question, you should see a feedback button. So if you notice any typographical errors in the question or the answer explanations after the question, send some feedback directly to Knewton's support. And hopefully they'll get back to you pretty quickly and help you fix whatever issue needs fixing. Now, this instructor cheat button will not be there for you as a student, so I'm not going to use it myself. And then next to that, you will see, though, more instruction. So if you're working on a particular question in a particular objective that you're having trouble with or you don't remember the material too well, pull up more instruction here, click on this, and they'll provide you with some reading to do or videos to watch or both that are related to that particular objective. And then hopefully having that instruction up will help you get through the problems in the assignment. All right, so before I actually get into any of the questions, I'm going to simply go over, first part of the video here, the derivatives, all right, which will give us slopes of tangent lines to the curves of the trigonometric functions, right? The 6 trigonometric functions. Now I'm going to be writing trig here instead of trigonometric, right? Usually trig abbreviates trigonometric. So derivatives of the trig functions. I'll also remind you going to Desmos, so I don't have to waste too much time drawing them myself. I'll remind you of what the graphs of these functions look like as well. All right, so we're going to start with the sine function. So say we're given, f of x or y equals the sine of x, where x is in radian measure. You're going to notice that in all these, anytime you're working with the trig functions and calculus here, for the most part, I'd say 99% of the time, the inputs will be in radian measure, not degrees. So just reminding you of what that looks like real quick. So here's, the desmos.com, right, free online graphing calculator site. I'm already in radian mode, right? If you go to settings off to the side here, make sure you're in radians. So I got f of x equals the sine, sin of x. And remember, it's this wave. You have 0, 0, pi 0, right? There was an x-intercept every pi radians. Pi over 2, 1, negative pi over 2, negative 1. It had a period of 2 pi, right? Every 2 pi radians, the wave just repeated again. And the highest it got was 1. The lowest it got was negative 1. Again, hopefully this looks familiar from a previous, pre-calculus or trigonometry class. All right, so we'll start with sine. And I want to find, the derivative function f prime. So for just sine and cosine, I'm going to be using the limit definition of a derivative because we don't really know anything about these yet. So remember that definition of the derivative we saw in a previous video, the limit definition. So this was one of them. Take the limit as h approaches 0 of, and then the slope of any secant line on the graph of sine. So that would be take the value of sine at x plus h minus, and then the value of sine at just x. So again, 1 point at x, 1 point at x plus h. So there's the rise, and then divided by the run, which would be h, right? X plus h minus x. So if I were to put in 0 for h, right, this is, you'd have 0 in the numerator, 0 in the denominator. Remember those 0 divided by 0 limits were indeterminate. So I had to retool this. So look at this first part here, this first term up top. That's the sine of a sum. So I'm not going to get into all this, why this is. This should have, this is something that should be known from a trigonometry class or pre-calculus class. But remember, the sine of a sum of two quantities was equivalent to the sine of the first times the cosine of the second, so the sine of x times the cosine of h, then plus, and then the sine of the second quantity, so sine of h times the cosine of the first, right, cosine x. So again, hopefully that rings a bell in some way. Again, I'm not going over improving this or demonstrating why that is. All right, so that's a way to retool, rework the sine of x plus h, sine x cosine h plus sine h cosine x. Then we have minus the sine of x. All right, that was the second term up here. And then all that, divided by h. All right, so it's still in a form where if I were to just, plug in 0 for h, or cosine of 0 is 1, so this would be sine x, and then take away sine x over here would be 0, and sine of 0 is 0. So you still have 0 in the numerator, 0 in the denominator. So I still got to retool this, rework this. So the way we're going to do that is notice how the first term up there and the last term up here both have a common factor of the sine of x. So I'm going to group these two terms, factor the sine of x out, and what would be remaining would be the cosine of h minus 1. So factoring out the sine of x from this first term and last term, the other factor is, the cosine of h minus 1. Again, everything up here is getting divided by h, so I can do this. This is getting divided by h. That's the first two terms, all divided by h there, but I'm strictly going to put it under this factor here. Right, then plus, and then this term in the middle, we have the cosine of x is one factor, times, and then the sine of h, and again, this factor, this term is getting divided by h as well. I'm just going to pop it under this sine of h factor. Okay, so this is another way to rewrite what I have up here in the middle line. And then something that came up in a previous chapter, previous video on limits, some special limits. You may recognize these. So remember this one here, I'm boxing this in. Sine of h divided by h as h approaches 0. So that, remember that limit, that expression would approach the value of 1. And then this, another special limit involving trig. You have the cosine of something minus 1, or 1 minus the cosine of something divided by that same thing inside the cosine. So your cosine h minus 1, all divided by h. And that expression inside the cosine there and in the denominator is going to 0. Remember that expression was approaching a value, or had a limit of 0. So putting all this together, we end up with the sine of x, because again, this sine of x doesn't change, right? The only thing we're changing here is h. H is approaching 0. So anything that's not h will be considered constant. So this sine of x is considered constant. So it's the sine of x times, and then this limit here in the box, right, with the cosine h minus 1 over h is 0. Then plus, and once again, cosine of x, right? This does not have h involved, so it's considered constant. So that'll stay cosine of x times, and then this sine h divided by h factor approaches 1 as h approaches 0. So overall, we have, first term is 0 plus second term is the cosine of x. So you end up with just the cosine of x. All right, so I'll box this in. All right, so that's a nice result. The derivative of the sine function. So again, f prime here is the cosine function, right? How nice is that? I would suggest you get to memorizing this, make flashcards, do whatever you got to do, repeat it over and over again every time you use it. Get to learning that. All right. So the derivative of sine is cosine. All right, so I'm going to do something similar for the cosine function next. So now I'm working with the cosine function. So again, let's say we start off with equals the cosine of x. Once again, just to refresh your memory as to what this looks like. This is another wave, right? So here I am back at Desmos. Just changing sine to cosine here, and still another wave, right? And you see that instead of 0, 0 for the y-intercept, you got 0, 1. Cosine of 0 was 1. And all of the x-intercepts occurred at odd multiples of pi over 2, right? So negative 1 pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, right? Odd multiples of pi over 2. The period was 2 pi again, right? So starting up here at 0, 1, here's 2 pi 1, right? That piece of the wave just kept repeating over and over again, had a period of 2 pi. And highest it got is 1, lowest it got was negative 1, just like sine, right? Very similar to the sine function, right? So that's the cosine function again, the look of it. All right, so once again, I'm going to find the derivative of the cosine function using that limit definition. All right, so f prime would be the limit as h approaches 0 and then again, slopes of secant lines from a point at x to a point at x plus h on this cosine graph, right? So the rise would be the cosine at x plus h minus, and then the cosine at x, and then all that divided by the run x plus h minus x, or just the h again. All right, so like before, like all the derivative setups with this limit definition, you have if you were to plug 0 in, even though technically you're not, so h is approaching 0, but if you were to ignore that and actually plug it in, you'd end up with 0 in the numerator and 0 in the denominator, right? Some undetermined, indeterminate form, something that's nonsensical, doesn't tell you anything. So I got to retool this expression, rewrite it in some way that'll make more sense. The limit as h approaches 0, and then like with the sine of a sum, here I have the cosine of a sum of two quantities, x plus h. So again, I'm not going to go into why this is. I'm not proving anything. This should be known from a trig class or pre-calculus class. So that's the cosine of the first value. So cosine of x times the cosine of the second value. So cosine x times cosine h. Then for the sums, it was is minus, and then the other way around with sine, right? So sine of x times sine of h. All right, so this expression here, cosine x cosine h minus sine x sine h, is equivalent to the cosine of x plus h. All right, then you have still the minus, cosine x there. And all this, right, divided by h. And once again, even after that retooling, if h went to 0, you just made h 0, you'd have 0 in the numerator, 0 in the denominator. But like before, there are some terms that have a common factor, right? This cosine x is in the first and third term. So I'm going to rework this. So we have the limit as h approaches 0. So from these two, factoring out the cosine of x, times, and if I remove the cosine of x from both those factors, the other factor would be cosine h minus 1, quantity cosine of h minus 1. And then this is gain divided by, put this divided by h under this factor with the other h in it. And cosine of x would be treated like a constant, because again, h is changing, not x. Then we have, minus this second term here, this, sine x sine h. So again, minus sine of x times the sine of h. And this is also gain divided by h, and once again, I'll just throw that divided by h under the factor of the sine of h. And then you see some pretty familiar stuff, just like in the derivative of the sine function earlier. I see this sine of h divided by h. H is approaching 0, so that will be approaching 1, or have a limiting value of 1. And then this first term has a factor of this cosine h minus 1 divided by h. Again, h is approaching 0, so remember this will approach 0 as well, right? It has a limiting value of 0. So overall, we end up with the cosine of x times 0, so that'll be gone, then minus the sine of x times 1. So 0 minus sine x, or just minus sine x, are the opposite of the sine of x. So here's another one. Know all these. So if you're given the cosine function, the derivative, right, the first derivative, f prime here, is the opposite of the sine function. So negative sine or opposite of sine. Again, I'll box that in. That's another important one. Now, I did the limit definition of the derivative for the sine and cosine just now. And derivative of sine is cosine. Derivative of cosine is the opposite or negative sine. Now, once you know these two, once you know the derivative of sine and cosine, you can use the quotient rule to help you find the derivatives of all the other ones. So I'd highly suggest knowing at least the derivative of sine and cosine by heart. All right, so now I'm going to move to tangent and cotangent. All right, so the tangent function. So again, that's f of x equals tangent of x. And once again, a quick little refresher as to what the graph of this would look like. So changing cosine here in Desmos to tan, right? Tangent of x. All right, so this had all sorts of vertical asymptotes. So remember the x-intercepts, or wherever sine was 0, because we'll see in a second, I'm going to rewrite that. Remember, tangent was sine divided by cosine. So wherever the sine was 0, the numerator, you had an output of 0, so multiples of pi. And then you had these asymptotes at wherever the cosine was 0. So say x equals, pi over 2. See that blue line that just came up there? That'd be a vertical asymptote. X equals 3 pi over 2, negative 1 pi over 2, asymptote. So remember, anywhere the cosine was 0, you had one of these vertical asymptotes. The tangent was undefined, going to either infinity on one side or negative infinity on the other. So, then it could get as high as you wanted, as low as, again, negative infinity to positive infinity. So domain was everything but odd multiples of pi over 2, and the range was all real numbers. So anyway, the derivative. So again, I can set up the limit definition. You could. You can go about it if you remember your trig stuff real well. Tangent of a sum and all that. But if you already know the derivative of sine and cosine, remember how to rewrite, you can rewrite the other four using sine and cosine. So remember the tangent of x would be the sine of x divided by the cosine of x. And now I have a fraction, right? Something that I would then apply the quotient rule to, right? So I'm going to use the quotient rule for derivatives. So again, I'm not going to rewrite what that is. That's been brought up in previous videos. I'm just going to say it as I do it. So then f prime, right, our derivative of the tangent function using the quotient rule, right, make a big bar up top here, right, the denominator the way it was times the derivative of the numerator, right, and we just saw the derivative of sine of x is cosine of x, then minus, and then the numerator the way it was, sine of x, times, and then the derivative of the denominator is the derivative of cosine of x, which we just saw is negative sine x, or the opposite of the sine of x. And then all of that divided by the denominator the way it was, cosine x, squared. All right, so this is all well and good. I mean, this expression is the derivative of the tangent function. It's just this is much more easily written using some trig identities. So up top here, cosine times cosine, that's, cosine of x squared, but remember how they usually put the power right after the name for the trig functions, right? So this is cosine times cosine, cosine squared. And then I have negative sine x times another negative sine x, so we got plus sine squared, sine of x squared. And then down here, similarly, as I did with cosine earlier, right? This is cosine times cosine, cosine squared. So, cosine squared down here. And then some trig identities popping up here. So up top, so remember for any input, if you take the cosine of that input squared plus the sine of that input squared, you always get 1. And this is trig stuff. I'm not going over all that, right, proving it or anything. So the numerator is always 1. And then you have divided by cosine squared. So this is a lot simpler than what I had up here after applying the quotient rule. It's just there's an even quicker way to write this. So you may recall again that, remember, 1 over cosine is secant, that SEC. And this is, 1 over cosine squared. So the derivative of the tangent function would be called the secant of x squared. It's 1 over cosine times 1 over cosine again, or 1 over cosine squared. But here is the derivative of the tangent function. So again, if you memorize this, that'll make things faster for you, of course. But you can always do, what I did here if you want, as long as you know the derivative of sine and cosine, and the quotient rule, of course, at least that much. All right, so I'm going to do something very similar for the cotangent function. So that's here, f of x equals, COT, right, cotangent of x, which, remember, this is the reciprocal of the tangent function, so you flip over the tangent function. So this would be the cosine of x in the numerator divided by, the sine of x in the denominator. So again, a quick recall of what the graph of this looks like. So now the denominator is sine. So wherever the sine is 0, that's where the vertical asymptotes will be. So at 0, pi, 2 pi, multiples of pi. And wherever the cosine was 0 is where the x-intercepts, where the output's 0. So those odd multiples of pi over 2. So look, so go back here. I'm just going to change this tangent in Desmos to cotangent, COT of x. And now you see the x-intercepts, right? The points where the output is 0 are at the odd multiples of pi over 2. The vertical asymptotes where it's undefined are now at multiples of pi, right? There's that green line, x equals pi, x equals 2 pi, x equals 0 pi, or just 0, negative 1 pi, right? Those are where all the asymptotes are. And again, it's going up to infinity or down to negative infinity on either side of these asymptotes, so the range was all real numbers. All right. But anyway, so the derivative. Once again, if I think of this as cosine divided by sine, I'm going to apply the quotient rule once more. You could also, since you now know the derivative of tangent is secant squared, you could rewrite cotangent as 1 divided by secant, 1 divided by tangent, right? Cotangent is 1 divided by tangent, and use the quotient rule with that fraction. Either way, you'll end up with some equivalent derivative. All right, so f prime here, all right, our derivative of the cotangent function. And using the quotient rule, so again, denominator times the derivative of the numerator is, the opposite of sine or negative sine. Then minus, and then the numerator, cosine x, times the derivative of the denominator is cosine x, right? Derivative of sine is cosine. And then all that divided by, the denominator the way it was, squared. So there's your derivative of the cotangent function, right? But it's sloppy, right? There's a lot of it. It's not pretty. So going through this, you get this first one, sine times negative sine. That would be the opposite, or negative sine squared. And then minus, cosine, cosine, so cosine squared of x, and then all that, right? And then sine squared down here, right? Sine squared. And now this expression up top, and this is always -1, or if you were to factor -1 out, then you'd have sine squared plus cosine squared, which is always 1. So you have, -1 in the numerator all the time, no matter what x is. And the denominator is, sine squared. And this is great too. Again, this is nice. This is clean. It's definitely less complicated looking than the original after the quotient rule. But the way you're going to see it most often is I've got, negative, or the opposite of, and then 1 divided by sine. Remember that was cosecant, CSC of x. And it's 1 over sine, squared. So 1 over sine times 1 over sine again. So this would be negative cosecant, CSC of x squared. Right, so here is the derivative of the cotangent function, the opposite of, cosecant squared. Okay, good. All right, so there's 2 more. There are 6 of these. So again, I'm going to use the quotient rule for each of them. Right? Each of these last 4. So now we'll work with the last 2, the secant, right? And cosecant functions. So secant first. So I'm going to say we have f of x or y equals, remember that secant was sec of x, which, remember, this is the reciprocal of the cosine function. This is the way that was defined. So 1 in the numerator divided by cosine of x in the denominator. So again, I'll show you the graph real quick. So remember, this has a denominator of cosine. So wherever the cosine was 0, so those odd multiples of pi over 2, that's where this graph had asymptotes. And remember, cosine was always between, from between -1 and 1. So if you flip all those numbers over, take their reciprocals, you're always going to be higher than 1 or lower than -1. Right? You'll see that here. So changing cotangent back here to SEC for secant. And you see these, opposing U shapes, U up, U down, U up. Again, no x-intercepts, right? The graph is either 1 or, has an output of 1 or higher, or -1 or lower. And the vertical asymptotes, again, were at the odd multiples of pi over 2. So domain was everything except the odd multiples of pi over 2. And the range is values, from -infinity up to -1. And then again from 1 to infinity, but nothing in between. Right, so hopefully that looks familiar. But now for the derivative. So I'm just going to write the word quotient here this time, right? So we rewrote secant as a fraction. So I'm going to apply the quotient rule once more. So again, derivative f prime, it's the denominator, so cosine of x, times, now the numerator is a constant. So the derivative of the numerator is 0. So that'll be nice. This first term up here will go away. And minus the numerator, so just 1 times, and then the derivative of the denominator, right? The derivative of cosine was negative sine, or the opposite of sine. And all that divided by the denominator squared, and again, I'll put the square there, right? So cosine squared. So if you look at the numerator, simplify, you got 0, and then plus, right? Negative, negative. So plus the sine of x, so sine of x. You have sine of x in the numerator divided by cosine squared in the denominator. And once again, this is fine. If you know just this, that's better than most. But you can rewrite this in a simpler way, and the way they're typically going to rewrite it is after this. So you can rewrite sine over cosine squared as 1 over cosine times sine over cosine. Right? If you multiply these numerators, you get sine of x. You multiply these denominators, you get the cosine squared. So the way you're typically seeing the derivative of the secant function is, you see one of these factors is 1 over cosine, which is secant. So secant x times, and then the other one's sine x over cosine, so times tangent x. So this is what you're typically seeing in a derivative table. So if your function's the secant function, the derivative, the first derivative is itself, right? It's secant again, but then don't forget the times tangent. All right, so one more, and then we'll finally get back into the questions of the assignment. So again, very similar. I'm going to do the quotient rule once more. So this is cosecant. So this is, f of x, or y equals, and that was that CSC again of x, which, again, cosecant, the way it's defined is the reciprocal of the sine function. So 1 divided by sine. All right, so this has sine in the denominator. So wherever the sine is 0 is where you're going to have those vertical asymptotes, right? The graph will be going up forever or down forever on either sides of those. So that's at those multiples of pi, 0, pi, 2 pi, 3 pi, and so on. And once again, since sine is always between -1 and 1, you're flipping those numbers over, taking the reciprocals. This will be 1 or greater, or -1 or less, but not, not between -1 and 1 anymore. So I see that here. So you got a very similar picture with the cosecant, right? When I go CSC, it's this, U down, U up, U down, and there's again 1 and up, -1 and down, right? Nothing in between. And the asymptotes at, multiples of pi, 0 pi, 2 pi, and so on. All right. So again, just to refresh you as to what those look like. So now quotient rule once again for the derivative. So f prime, big quotient rule thing, you got the denominator as it was, the sine of x times the derivative of the numerator is 0. Right? The numerator is a constant, it's 1. Then minus the numerator, so 1, times the derivative of the denominator, right? The derivative of sine is cosine. And then all that divided by the denominator, which is sine squared, right? So let's put the square there, sine squared. So yeah, so up top, first term is 0, and then you got minus cosine x, so negative cosine x, or the opposite of the cosine of x, divided by sine squared. And like I've been saying, this is perfectly valid as the derivative of the cosecant function. It's just the way you're typically going to see this. It's, this is negative And then you have a product of a couple of fractions here that'll make cosine over sine squared. You could rewrite this as 1 over sine multiplied by, and then cosine over sine. And if you were to multiply the numerators, you get, negative cosine. You multiply the denominators, you get your sine squared. So what you're going to see in most derivative tables, and what I would suggest you remember, I would highly suggest you just remember all 6 of these eventually, is, the derivative of the cosecant function is negative or the opposite of, and then you have 1 over sine, which is cosecant again. So you see cosecant again show up in the derivative, but then there's another factor, right, times this cosine over sine, which remember that's cotangent of x. So here's what I would suggest you remember, right? Again, make flashcards, write them out a bunch, keep repeating them every time you're using them. Get used to them, and if you get to memorizing them, it'll make things a lot faster for you in the future. All right, so we got all 6 now. So I'll say them out loud real quick. Derivative of sine, cosine. Derivative of cosine, negative sine, or the opposite of sine. Derivative of tangent was secant squared. Derivative of cotangent was negative, or the opposite of, cosecant squared. The derivative of secant was secant times tangent. And finally here, the derivative of cosecant is the opposite of, or negative, cosecant times cotangent. All right, so now that we have all 6 of them, let's get back to the assignment. All right, so here was our first question. All right, this is find the derivative of other trigonometric functions. So this is the other 4 besides sine and cosine. But you see some cosine show up here, so that's why I wanted to just do all 6 of them initially. So we're asked to find the derivative of the following function, which has, some fraction with a combination of trig functions. You're seeing cosine in the numerator, and there's a cotangent of x, then minus 2 in the denominator. So we have f of x equals, and cosine of x in the numerator, and divided by the cotangent of x minus 2 in the denominator. So it is definitely a fraction, right? So I'm going to be applying the quotient rule again. So you're seeing or hearing the quotient rule a lot in this video. Hopefully it helps you remember it. So f prime in big bar here. So again, it's the denominator the way it was. So this whole cotangent of x minus 2, that whole thing, times the derivative of the numerator. The derivative of cosine is negative sine, or the opposite of sine. So negative sine of x, opposite of sine of x. So there's denominator times derivative of the numerator. Then minus, then the numerator, so the cosine of x, just cosine x, times, now the derivative of the denominator is a sum or a difference, so I can go term by term. Remember, the derivative of cotangent x is negative, or the opposite of cosecant squared of x. And then minus 2 is 0. Right? So that's all there is to that derivative, right? So you have denominator times derivative of the numerator minus numerator times derivative of the denominator, and all that divided by the, the denominator the way it was, right? So this entire cotangent of x minus 2 squared. Now, if you'd like, you could simplify this a little bit. Maybe distribute the negative sign, but to be honest, I don't really want to rewrite this in any way. Now, if we were asked to find the second derivative for some reason, I would go about simplifying this, but I am going to type in this, because that is the derivative function, right? It may not look as simple as you'd like it, but it is the derivative. So I'm going to type that as it looked here where it says, f prime of x equals. You gotta be careful with the fractions, so I'm going to be a set of parentheses. So everything inside this first set of parentheses is going to be in my numerator. So this is all in the numerator. So you got the denominator, so another set of parentheses, cotangent of x minus 2 times negative sine x. All right, that's the denominator times the derivative of the numerator, minus, then the numerator, cosine x, times, the derivative of the denominator, negative cosecant squared x. I'm hoping it takes the square like that. We'll see if it does. All right, so that should all close out the numerator, right? So I closed that big set of parentheses. So that's all in the numerator. See, now when I hit divide, all that's above the bar, right? Make sure that entire expression there is above the bar. And then down in the denominator, right, you have the original denominator, the cotangent of x minus 2, that entire thing squared. See, so you can, as long as you know the rules, right, you know how the quotient rule is supposed to work, you can type in what you're doing in the quotient rule or the product rule or whatever rule you're using. Type it in as you use it, and as long as what your expression is equivalent to what they have, and look, that's exactly what they have down here pretty much. They just put the factors in different orders for both these terms, but see, they didn't really simplify it either. All right, they just used the quotient rule and left it at that. Great. Now, after you get a question right or wrong, you'll be given some sort of answer explanation. I would highly recommend you read through these. If you got it right, just glance through it, see if they did something in a way that you like better than the way you did it. So maybe you can try their method for a question like that in the future. I would definitely, read through the answer explanations carefully if I got something wrong. All right, try to figure out where you went wrong, and hopefully you can learn from your mistakes for future questions of that nature. Right, so now I'm bumped over to this other objective. Remember, the Knewton Alta does this interleaving where it switches you on from objective to objective on occasion, switches up on you. So here's the objective: find the derivative of a sine or cosine function. So now I'm just going to see expressions that have sine or cosine in there somewhere. So here, another derivative where once again, I'm going to be using the quotient rule. This is another fraction. Now I'll just put the negative up top here. So the numerator is negative 2 times the cosine of x, and the denominator is a polynomial. So when I do the derivative of the denominator, I'm just going to be doing the power rule. Simple as that. And like before, when I'm done using the quotient rule, that's how I'm going to type it. I am not going to go about simplifying this thing. So f of x is, again, I'm putting the negative up top with the 2 cosine x. So we have a numerator of negative 2 times the cosine of x and a denominator of 7 times x to the 4th. So once again, fraction, I see a fraction, so I'm going to be applying the quotient rule when I go about stating the first derivative. So again, big bar. So it's the denominator, so 7x to the 4th, multiplied by the derivative of the numerator. So remember, coefficients stick around, so that'll be negative 2 times, and then the derivative of cosine was negative sine. So this is positive 2 sine of x. Now, if you want to make the 7 and the 2 there into 14, multiply those, you can. So maybe I'll do that when I'm typing. Then minus, and then, leave the numerator the way it was. So -2 cosine x times the derivative of the denominator, which again, this is a little polynomial term here, just do the power rule. So 7 times 4, x to the third, so 28 x to the third power. So again, all that in the numerator divided by the denominator, 7x to the fourth, squared. So again, this is great. You can type this the way it looks. That is the derivative function. Now I can make 7 times 2 into 14. I can make this +2 times 28 +56. So I might do that. And then down here, 7 squared is 49. X to the 4th squared is, x to the 8th. So I'm going to write that as 49 x to the 8th, right? Just to save a little time on typing. Yeah, so make sure when you have multiple terms in the numerator, the entire thing is in parentheses, right? So that way when you hit divide, it'll all be up there. Or you can use, right, this, there should be some fraction thing. Well, I'm not seeing it here. Maybe it's in this other keyboard. Nope. All right, so, yeah, whatever. So make sure you have parentheses around your entire numerator. So again, my first term, I had the 7 times 2 is 14, right? So 14, then you have x to the 4th is another factor in that first term, and then you have sine of x. All right, then the coefficients of the second term, you have minus, and then -2 times 28, so that'd be plus 56, right? -2 times 28 times -1. And then there's an x cubed there, and then there's a cosine x there, right, for factors of that second term. So all that was my numerator. Divided by, and then the denominator, right, 7x to the 4th squared would be 49x to the 8th. Now you could simplify this further by factoring out x cubed, even factoring out 7x cubed, but I'm not going to do that. As long as what you type in, see, they did the thing where they factored out 7x cubed. All right, that would have simplified to this. 2x sine x plus 8 cosine x all over 7x to the 5th. That's if they factored out the 7x cubed from the terms in the numerator and, cancel some common factors with the denominator. But as long as what you type is equivalent, they don't say simplify at all, right? As long as they're not saying simplify, whatever you type, as long as it's equivalent to the right answer, you should be given the points. It should give it to you. So same objective here with the sine or cosine. All right, so this one is going to involve the product rule. So I'm not going to write the product rule out. I'm just going to say it. It's something you should know by now, or have seen a bunch, hopefully by now. So you see I got this polynomial factor, -6/5 x to the 4th, times cosine x. So it's a product of two different kinds of functions here. So I do need to go through and use, the product rule when stating the derivative. So f, again, it's called f. Right? So my first factor is -6/5 times x to the 4th, and then times, right? So again, this is going to be my first factor. I'll put like a big F next to that for first. And then my second factor, cosine x. Right? So I'll put a big S under this for second factor. So again, this is a product for sure. Right? It's not adding or subtracting. There's definitely times in here, right? So I'm going to use the product rule for derivatives. All right, so f prime, and it's leave one of these the way it was. So I'm going to leave the first one alone. So -6/5 x to the 4th times, and then the derivative of the other one. So I leave the first factor alone times the derivative of cosine. The derivative of the second factor is that negative sign, or the opposite of sine. and then plus, and then do the other way around. Take the derivative of the first. So this would be, power. I would just do the power rule with this as a polynomial. So it'd be negative 24/5 times x to the third. All right, so there's the derivative of the first, and then times and leave the other factor the way it was, cosine x. And if you'd like to simplify a little bit, maybe with just the coefficients, got -1 here, -6. So I'll make that positive 6/5 times x to the fourth times sine x in this first term. And then the coefficient of the second product would just be -24/5. So I'll make this -24/5 times x cubed times cosine x. But this is pretty much, what I'm entering. That is the first derivative function. All right, so again, positive 6/5, right? Because it was negative times negative. X to the fourth times the sine of x for the first term. And then, minus 24/5, -24/5 was the coefficient of the next product times x cubed times the cosine of x. And that should cut it. All right, great. All right, so they did the other order. Remember when you add, you could put the terms in either order. It's the same result. All right, so now it's find a tangent line, right? The line tangent to a trigonometric function. So here I'm going to go to Desmos, and we can actually see the tangent line, right? We'll see the line going through a point on the curve that points in the direction that the curve is going at that moment, right? The line tangent at that point. So find the equation of the line tangent to the graph of this function involving cosine, and at the point where x equals -pi/4. And we're asked to enter an exact answer, right? So that means don't round so many decimal places, don't punch things into a calculator and round, right? Just enter things as they are exactly, right? All right, so remember what you need two things to write the equation of a line. So the function we're given, and we'll look at the graph of this in Desmos in a second, but this is f of x equals, 1 plus 2 times the cosine of x. And we want to find the tangent line at the point where x equals -pi/4. All right, so remember for a line, you need two things. You need the point. So we know the x coordinate of the point, right? They gave that to us, -pi/4. Now I just need to plug it in and see where we're at on this function, right? What's the y coordinate? So what is f of -pi/4? So I'll do that off to the side here. F of -pi/4 be 1 plus 2 times the cosine of -pi/4. So again, I'm not going to go into the unit circle and all that, right? This is not a trig lesson. These are things you're kind of expected to know. Remember the cosine -pi/4, that's like -45 degrees, right? That would be the square root of 2 divided by 2. Or 1 divided by the square root of 2, whatever. And then you see how the 2's would cancel now in this second term. So the output is simply 1 plus the square root of 2. So here's the point on the curve. -pi/4 for the x coordinate, and then this 1 plus the square root of 2 for the y coordinate. And I'll show you that. I'll show you that on Desmos that is a point on this curve. So here's the function we're given. F of x equals 1 plus the cosine, 2 times the cosine of x, sorry, 2 times the cosine of x. So this is wavy curve thing, right? Cosine graph. And then here's the point. I'll plot this point. Negative pi, you can just type pi, negative pi over 4, comma, and then 1 plus the square root, just sqrt, square root of 2. And here I'll label it. Now they're rounding it here. See, this is what they don't want in the assignment. See, this is estimated 2.4142, right? That number is an estimate. That is not exact. Exact means just write 1 plus the square root of 2, right? Leave it as it was. Now, if you look at this graph here at this point, you see how the graph is, going up at this moment. So if I were to draw, when we get the equation of our tangent line, it should have a positive slope, right? So that's what I need next, the slope. So I've got the point. Now I want the slope, and remember the slope of any tangent line was the derivative, so f prime, and I need f prime at this, negative pi over 4 value, right, at that point. So going up here, right, we got f of x is 1 plus 2 cosine x, f prime at any x. Now this isn't a product or a quotient or anything, thank goodness, right? So it's just 0 for the first term, plus, and then 2 times the derivative of cosine, which was negative sine. So this would be negative 2 times the sine of x. So going down here, plugging in negative pi over 4, we get negative 2 times the sine of negative pi over 4, or negative 45 degrees or whatever. So again, this is something you should know how to find or remember. Got your unit circle in your head or something, or you wrote it out somewhere, but I'm not going over all that. So we end up with negative 2 times, and the sine of negative, pi over 4, or negative 45 degrees, that was negative square root of 2 divided by 2. So you get the 2 cancels here, and negative times negative is positive, so the slope is positive square root of 2. So here, putting all this together, right, putting all this information together, gives us our tangent line. Now I'm going to start it off in point slope form. So remember that's y minus the y coordinate of my point, the entire y coordinate. That's why I'm putting in parentheses, right? The y coordinate of the point is this 1 plus square root of 2. So y minus the y coordinate of my point equals the slope, which is the square root of 2 again, times the quantity, and then x minus the x coordinate of my point. But if I do x minus negative pi over 4, that's x plus pi over 4, right, minus a negative. Now they have y alone, so I'm just going to add this 1 plus the square root of 2 to both sides. And if it's being added, there's really no need for parentheses around it. So we have y equals, again, the slope, square root of 2, times, x minus my x coordinate, so x plus pi over 4, minus negative pi over 4, in parentheses, and then, plus the y coordinate of my point was 1 plus root 2. Again, no need for parentheses around that. It's being added. There's nothing multiplied by it, nothing subtracted, nothing raised to powers. So this is what I'm going to enter. Now you could distribute the square root of 2 if you wished, but as long as you have y equals and then everything else without y on the other side, that's as long as it's equal to what they have, right? Just like all the other ones, you should be fine. So back in the assignment, right, I'm going to see I got the y equals already, so I'm just typing the other side. So again, square root, oh, that doesn't work here like in Desmos, so I gotta go square root symbol in the little keyboard there. Square root of 2 for the slope times the quantity, and then x, minus a negative, so x plus see, pi is here, right? Pi over 4, close parentheses, and then we're adding, the y coordinate of our point to this side, 1 plus the square root of 2. And before I hit submit, let's actually see. So I'm just going to copy and paste this into Desmos. So before I submit this, let's go to Desmos here. I'm going to put this in y equals, and then I just paste it. And look at this red line that just showed up. Look at that. That is definitely, you zoom in closer and closer to that point. You see how the line, that red line, is definitely pointing in the direction. It's tangent to the curve, pointing in the direction of the curve at that moment. And the closer and closer you zoom into that point, the better the line is at being like the curve, right? It's almost exactly like the curve the closer you get to that point. All right, so that's a great equation for our tangent line. And so this should be good. So I hit submit. Wonderful. So I'm assuming they're going to have a distributed, they distributed the square root of 2 there. But it's the same expression, right? It's something equivalent. All right. Another tangent line problem, this time with a cotangent function, and it's a little different where it's, one of those interactive ones. So it looks like it's kind of like Desmos here. I think you're playing around with some Desmos stuff in this little snippet. So let's do this first. All right, so let's find the equation of the line tangent to the graph of f of x equals -2 times the cotangent of x and then minus pi minus 1 at the point where x equals -pi/4. So then we're going to move some points around though, right, so that the red line on the graph matches the equation that we get, for our tangent line. All right, so the function we're given, so f of x equals -2 times the cotangent of x, then minus pi minus 1. And we're talking about at x equals -pi/4 once again. So first, the point. So -pi/4 for the x coordinate, right? And then when I plug -pi/4 in, right, I'll do it over here. F of -pi/4 be -2 times the cotangent of -pi/4, and then you got minus pi minus 1. This cotangent of -pi/4 or -45 degrees, remember that's -1. That's -1. So this is -2 times -1, and then you got minus pi minus 1. So this is 2, then minus 1 over here makes 1. So we end up with 1 minus pi for the y coordinate. Again, I just want to show you that that's actually on there, right? We'll verify this with Desmos. So again, they already got this graph in the little snippet in the problem too, but I'm going to type it again here. So you got f of x equals, -2 times the cotangent of x minus pi minus 1. Right, and zoom this out, go home here. So you see that's what you're seeing in the assignment, right? That the blue graph there. Now I'll plot the point as well. All right, I said the point that we're at is at, -pi/4, comma, and then 1 minus pi. You see this, I'll label it, right? Now they have all sorts of, crazy decimal there, -2.14159, right? That's, we're not doing that, right? We're typing in, well, we're not typing anything. We're going to be moving some points on a graph. So what I want is the tangent line, right? I want the line tangent to the graph at this point. Now, when I do draw the tangent line in, it looks like it should have a positive slope again, right? It should be sloping upward. The curve is going up at this moment. So let's find that. So now the slope. All right, so the derivative f prime at x, at any x, Going to be -2 times, and then we saw before, right, the derivative of cotangent was negative or opposite of cosecant squared. So -2 times negative cosecant squared, that'd be +2 times cosecant squared. And then this here, I know there's a letter, it's pi, but this is constant. All right, there's no variable, there's no x in the rest of it, so the derivative of the rest of it is 0. So this is it for the derivative at any x. And then at -pi/4, 2 times, the cosecant of -pi/4, but then that's being squared. So it's 2 times, the cosecant squared, right? So we take the cosecant first. So remember the sine, we saw the sine of -pi/4 was √2/2. Well, negative √2/2. It's going to be squared anyway, so it doesn't matter if it's positive or negative. But and then flip that over, that'd be 2 divided by the square root of 2, which is just the square root of 2, but negative. So you have negative square root of 2 for the cosecant of -pi/4. But that's being squared. So this is 2 times, 2 again. Right, when you square this, it's just +2. So you end up with 4. Slope of 4. All right, so the line would be y minus the y coordinate of our point, right, this quantity 1 minus pi here, equals the slope 4 times the quantity, and then x minus, -pi/4, so x plus pi/4 again. Whatever, I just want to make sure when I set up my line, all right, I'm going to set up this line so that it has a slope of 4. All right. So going back to the problem. So let me type this in and show you though. All right, so I got y minus, quantity 1 minus pi equals 4 times the quantity x plus pi over 4. It's about the same color. It's almost exactly the same color. Let me change the color on that to like red or something that contrasts with it. So look, see that red line that's there? You zoom in closer and closer to this point, definitely pointing in the direction that the curve is going in, definitely tangent to the curve at that moment. All right. So back in the problem. All right. So here. So they gave us the point. See how they have the point at -pi/4, and then this is 1 minus pi here, right? They already gave us the point. You can't move that one, but you can move this one, all right? Now it says to submit your answer by dragging the red point such that the drawn tangent line matches the equation for it. Now I think if I just move it so it looks tangent, because I don't know if I can get this exact, because to have a slope of 4, let's see, if I move to that would mean that I move right 1, up 4. Let's see if we can do that. Now if I move to the right 1, that would be, I don't know if you can move it perfectly like that. Yeah, it goes by nice values. Right, if I move, oh boy. So I think if you just move it so it looks like it is tangent, so maybe something like that. See how it's like, it looks like it's tangent. I don't think that's good though. It's really tough to move this to an exact point that's 1 unit to the right and 4 units up, especially where this is located. So I'd suggest just moving the point so that your curve, your line looks like it's, tangent to the curve at that moment and see what happens. No. Okay, so let's try. It says try again. All right, so I'm going to, let's see. I wonder if I can get a nice, Oh yeah, I can get a nice x-intercept here. Sorry. Sorry about that. Look, if I put this in slope-intercept form, like I probably should have in the first place, right? Distribute the 4, and you have y, minus 1, plus pi over here after distributing the negative, and over here you got 4x, and then you have 4 times pi over 4. The 4's will cancel. I'll be left with plus pi. Ah, look at this. See, if I subtract pi from both sides, pi will be gone. So, and then I just add 1. We get y equals 4x plus 1. That's an easy line to draw. So sorry, I was too hung up on leaving that in point slope form. See how this has the point, this has the point 0, 1 on it, right? The y-intercept would be 0, 1. So that should be an easy point to find. So there's 0, 1 right there. That's it. This line is the tangent line. You can see that here. So my apologies for a little snafu earlier. If you put it in slope-intercept form, it'd be easier to see then. Better. Great. And again, they probably go through it and put it in slope-intercept form. Yeah, see, they end up with slope-intercept form, not just point-slope form like I had, and it's very easy to see what the y-intercept is in that case and plot that. Great. All right, then this goes back to the other trigonometric functions, right? The 4 of them that aren't sine or cosine involved. But so you got here, the cosecant of x, but also this rational function, 1 over x to the 5th, right? That's not trig, but you may recall, from the power rule section or whatever, you could rewrite this as a power. I could use the quotient rule for this term, but you can rewrite this as a power and then use the power rule, right? A negative power. All right, so we have f of x equals negative cosecant of x plus 1 over x to the 5th. So remember, I'm going to rewrite this as negative cosecant plus, and then remember this 1 over x to the 5th is the same as x to the negative 5 power. Right? Negative powers are just reciprocals of the positive ones. And now I'll find the derivative. All right, go term by term here. It's just a sum. So f prime is, so this is negative. Now remember the derivative of cosecant was negative cosecant cotangent. So you have negative negative in front, so it'll just be positive cosecant x times cotangent x. Right, for the first term. That's coming from this first term. And then here, just using the power rule. So minus 5 times x to the negative 6, right? You lower the power by 1, subtract 1 from the power. And this is it. That's your derivative function, right? There was no product there. Again, I could have used the quotient rule if I left that term, that 1 over x to the 5th as a fraction. But it's a lot easier to take those like that, with just a single power down here, rewrite it as a negative power and apply the power rule. So we have just positive cosecant x times cotangent x, and then minus 5 times x raised to the negative 6. And again, you can keep negative powers and stuff, right, as long as it's equivalent to the right answer. All right, so now we get into higher order derivatives of sine and cosine. All right, so this is a little different than what we've seen. So let's get into these. So this is just for sine and cosine, though. So higher derivatives. So second derivative, third derivative, etc. of the sine and cosine functions, but just sine and cosine. All right. You're going to see some nice pattern forming with the sines and cosines. patterns that really don't form very easily. You're not going to see a nice pattern with the other four, right? Tangent, cotangent, secant, cosecant. So starting with sine. Okay, so again, the first derivative, so again, say we start with, let's do y equals sine of x, f of x equals sine of x. So again, that's you could call this the 0th derivative if you wish. Again, I'll put this in quotes because usually people don't say that, but we haven't taken the derivative yet, so it's like the 0th derivative. Then the first derivative, right? Now you could call it y prime, or remember this notation here. They're kind of having that pop out of you, dy over dx. Our first derivative is cosine x. So again, this is the first derivative. I'll just put deriv. And then the second derivative. So derivative again. So remember that notation was d2 over dx2, right? The d squared y over dx squared, even though these aren't squares, they're just indicating that you're taking the second derivative. Well, that's the derivative of cosine, which is negative sine. So again, there's the second, and put deriv. Third derivative, y triple prime, or that, d3y over dx3 there. That'd be the derivative of negative sine, which would be negative cosine. So there's my third derivative. And then the fourth derivative, now you can keep doing the primes or just write the number in parentheses up here. So that implies not to the fourth power, but the fourth derivative. Or that differential notation, that d notation, d4y over, dx4, right? So again, it's the derivative of negative cosine, which would be negative sine, so positive sine. And look, so again, there's the fourth derivative. So you see what happens is that these first four I had here, right, from the 0th to the third, these repeat every four. Right? So you see 0th derivative, 4 later, I'm back to sine. All right, the fifth derivative would be cosine. The sixth derivative would be negative sine. The seventh derivative would be negative cosine. These four, sine, cosine, negative cosine, keep repeating. So what you do, so for higher derivatives, so they're going to have this notation here, d sub n, dn, not sub n, super n. So the nth derivative of the sine function with respect to x or whatever the input variable is. So this is that notation with the dn over d, or you do the y with the n in parentheses like this, right, where y is sine of x. But the nth derivative of the sine, you divide n, right, what derivative you're taking, by 4, and then look at the remainder. What's left over? Remember, there's a quotient and a remainder when you do division. How many times something goes into something is the quotient, and then what's left over is the remainder. If the remainder is 0, then you're going to have sine, right? 0th derivative, 4. So basically, if n is a multiple of 4, 0, 4, 8th, 12th, 16th, your result is sine. If the remainder is 1, so you're 1 larger than a multiple of 4. So if n is 1 bigger than a multiple of 4, the result is cosine. All right, the first derivative would be cosine, the fifth would be cosine, the ninth, just keep adding 4 to that. If your derivative number is 1 larger than a multiple of 4, your result is cosine. If the remainder is 2, it's like the second derivative here, your result will be negative sine. And if your remainder is 3, you'll be like the third derivative here, where the result is negative cosine. All right, so this is key. All right, so that's for sine. Something very similar happens, for the cosine function. So I'll do that on the next page. So again, starting with the zeroth derivative where we haven't even taken the derivative yet. Right? So again, there's the zeroth derivative. Again, I'll put it in quotes because I don't think that's technically it's not a technical term. Zeroth. I guess people say it sometimes, but so yeah, so first derivative, right? Y prime or that dy over dx. So the first derivative of cosine is negative sine or the opposite of sine. Okay, so there's the first derivative, and then the second derivative, y double prime, or that d2y over dx2, would be negative cosine, right? The derivative of negative sine would be negative cosine. So there's the second derivative. And then y triple prime, right? The third derivative, d3y over dx3. The derivative of negative cosine would be negative sine, so back to sine. And then there's your third derivative. Then finally here, the fourth derivative, right, y4 here, or d4y over dx4. Derivative of sine is, cosine again. So you see how I've started over, right? Cosine here, and that's what I started with. So once again, these first four, from the, original, the zeroth derivative up to the third derivative, these keep repeating. You repeat every four. So again, the zeroth, the fourth, I'll write the fourth here. So the fourth, the eighth, the 12th, the 16th, the 20th derivative would all be cosine. So pretty similar to for the sine function, right? So when you're doing the nth derivative or that, dn of the cosine function, right, the cosine over dxn here. So again, you divide n by 4, right? Take the derivative you're taking and divide that by 4, and then look at the remainder. What's left over? If the remainder is 0, that means, n is a multiple of 4. Then your result, you'll be right back to where you started. You got cosine. If the remainder is 1, then you'll have, just like the first derivative, your result will be negative sine. So again, the first derivative, and then keep adding 4, right? Fifth derivative, ninth derivative, 13th derivative, 17th derivative would all be negative sine. If the remainder is 2, then it would be like having the second derivative here, negative cosine. So again, the second, and then keep adding 4, 6th derivative, 10th derivative, 14th derivative, etc. would all be negative cosine. And finally, if the remainder is 3, it's like this third derivative here, where your result is the sine function. So again, this is key for your higher derivatives of cosine. So like I said, only for sine and cosine will you see this repeating cycle of 4. So our example, the question in the assignment, we're asked for the 36th derivative of, now remember, coefficients like -7 would stick around. Right? Still have, no matter how many derivatives I take, that times -7 will stay there. That was the constant multiple rule. So I'll pull that out, keep it there. So we have this is the 36th derivative. So d36 up there over dx with the 36 up here down of, and then it's -7, times the sine of x. So again, the constant multiple rule, that -7 is going to stick around. So you take this derivative you're taking, right? 36. 36, when you divide it by 4, that's 9 with a remainder of 0. All right, 9R0, 9 with a 0 left over. 36 is a multiple of 4. And if you recall from my page earlier, right, if you're doing a multiple of 4 derivative, 0, 4, 8, 12, you're right back to where you started. So this will be the sine of x again. So again, the coefficient stays -7 times, and then the 36th derivative of the sine function would be the sine function again. So I just end up with that again. -7 sine x. So that's what I'm typing. So -7 times the sine of x. And great. So another one like this, but this time it's cosine involved. All right, so I'll do this on the same page I just had. Right, there's still some space. So here we're asked for the 14th derivative. So that d14 over, dx14 down here of the function -2, y equals, they have y here, but y is -2 times the cosine of x. So once again, coefficients, so this -2, stick around. All right, that's the constant multiple rule. So it's -2 times, and then the 14th derivative, right, the 14th derivative of cosine. So like I was saying, with these sines and cosines, take 14, divide it by 4. 14, 4 goes into 14 3 times with a remainder of 2, right? That's the key. All right, 3 times 4 is 12 with 2 left over to make 14. So that means that the 14th derivative of cosine is just like the second derivative of cosine, which would be negative cosine, right? Derivative of cosine is negative sine, which is negative cosine after that. So again, I got that on this page once again, all right? So the second derivative, negative cosine, right? If the remainder is 2, the result is negative cosine. So I have the coefficient, -2, times, and then the 14th derivative of cosine is negative cosine. And so we end up with +2 cosine x. So that's what I'm typing. +2 times the cosine of x. All right, great. All right, so now we're back to just plain old, here's some function, some expression with sine, cosine in it. So I've done a few of these now. Just gonna kind of say these at this point. We're like over an hour and a half in here. And this is just a sum. Now, if I had the product rule or quotient rule, I'd be writing it out, but this is just go one term, then the next term, and these are pretty simple functions. So like the derivative of 1/3 x would be 1/3. Right? 1/3 times 1. Plus, and then derivative of 3 cosine x would be 3 times negative sine x. So this will end up being -3 times the sine of x. And that's it, right? There were only 2 terms to go through there. It was a sum, and that's all. So here's one where I'll take you through. All right, it's got a fraction here, a quotient, definitely. I'll take you through it, but I'll just say it as I'm typing it, because I've done a bunch of quotient rule already. Now I'm going to put the negative sign. I'm going to imagine it's up there. You can either put it in the numerator or the denominator, but not both, right? That'll make it positive if you do it with both. So I'll put the minus up here with the x cubed. So the numerator is minus x cubed, or negative x cubed. And the denominator is 7 cosine x. I'm going to go through the quotient rule. So again, parentheses for everything up in the numerator. So it's denominator, 7 cosine x, times derivative of the numerator, which is negative x cubed, so negative 3x squared for the derivative of the numerator. All right, then minus, and then the numerator, negative x cubed times, and then the derivative of the denominator would be negative 7 sine of x. All right, that's all the numerator of the derivative here, divided by the denominator, so set in parentheses here, 7 cosine of x squared. So again, I just talked you through the quotient rule with this fraction up here. And you don't really, again, that's all you need. As long as you type in something equivalent to what they're going to have, should be good. All right, so here's another one where I'm just going to type it as I say it. All right, and again, I've done all these derivatives and stuff. Just gotta say it now. So this has two terms, but notice how the second term here is a product, right? This is a negative, this is 6x to the fourth times the cosecant of x. So I'm going to do the product rule when I get there. But for the first term, the derivative would be negative 2 times the derivative of cotangent, which was that negative cosecant squared. So this would be positive 2 cosecant squared of x. All right, so that's the first term. And now I'm going to do the product rule. So then plus, and then product rule with this, where my first factor will be 6x to the fourth, second factor cosecant x. So plus, and I'm going to leave the first factor alone, 6x to the fourth times the derivative of the second one, which would be negative cosecant x times cotangent x. All right, then plus, and then the derivative of the first, 6x to the fourth would be 24x cubed. And then, leave the cosecant alone, cosecant x. So there's the product rule applied to this. Now, if you want to put this minus out here, make this minus 6x to the fourth times cosecant x times cotangent x, you can. But I did the derivative of the first term plus the derivative of the second term, where I, use the product rule here, and that should be good. This is another one. It's just a simple two terms. Real simple, this one. No product rule or quotient rule necessary here. So just term by term, the first term, you got negative 2 times the derivative of cosecant is that negative cosecant cotangent. So this would be positive 2 times cosecant x times cotangent x. And then plus 4 times the derivative of cotangent, but that was negative cosecant squared. So you have minus 4 times cosecant squared of x, and that should be enough, right? There's only two terms there. All right, so here's another one where it says two terms. We saw something similar to this where you see this 1 divided by x to the fourth. You could use the quotient rule there, but I would rather think of this as x to the negative 4 power and then apply the power rule. Okay, so for that first term, derivative would be negative 2 times negative cosecant squared, right? So that's positive 2 cosecant squared. And then this next term, again, I'm thinking of this as x to the minus 4 power, negative 4 power. So when I apply the power rule, I bring the negative 4 down as a coefficient. So I got minus 4 times x to the, and then lower the power by 1. Negative 4 minus 1 is negative 5. So this next term would be minus 4 times x to the negative fifth. If you don't like the negative power, you can write this as minus 4 over x to the fifth. If you want to rewrite it with the positive powers, but that should be good enough. Great, so that objective's done. Once again, now this one has, and you go term by term here. All right, so remember 44 is a multiple of 4. Remember for the sine and cosine, if the derivative you're taking is a multiple of 4, the remainder is 0 when you divide by 4, you're right back to the beginning. So the derivative of the 44th derivative of sine is sine. The 44th derivative of cosine is cosine. So this is just going to stay the way it is. The 44th derivative of this function is itself, negative 10 sine x minus 8 cosine x. All right, real simple, that one. Here's the 15th derivative. All right, so a little trickier this one because 15 is not a multiple of 4. All right, it's 3 times. So this one I'll write out. All right. This got a sum. You gotta go term by term here. So we're taking the 15th derivative. So it's d15 over dx15 here of -5 times the sine of x, then plus 13 times the cosine of x. So again, the coefficients will stick around. You got -5 times. Now think of 15, right? We're taking the 15th derivative. 15 divided by 4. 4 times 3 is 12. And your remainder is 3 this time. So the 15th derivative of sine and cosine is going to be just like the third derivative. Now the third derivative of sine is, you got sine. The first derivative is cosine, second derivative is negative sine, third derivative's what did I say? First derivative is cosine, second derivative is negative sine, third derivative is negative cosine, right? So this would be negative cosine, the 15th derivative of sine. Which again, I had that paper here somewhere, right? Yeah, right here. So I'm checking this again, right? And the remainder was 3 negative cosine, right? When we're doing the 15th derivative of sine. Then you got plus 13 times, and then whatever the 15th derivative of cosine is. So again, it'll be just like the third derivative of cosine. So first derivative is negative sine, second derivative negative cosine, third derivative plain old sine. Right, so sine of x for that. And check my paper earlier. Here it is. So again, when you're doing this for cosine, if the remainder is 3, the result is sine, right? It's like the third derivative. And there we go. So we got, -5 times -1. This is +5 cosine of x plus 13 sine of x, right? So here's what I'm typing for the 15th derivative of that function they gave us. So 5 times the cosine of x plus 13 times the sine of x. Wonderful. All right. None of the tangent line stuff, right? So there's another one where this time I'll probably let me rectify my mistake from earlier, and let's put the tangent line in slope-intercept form. That should make moving this point around a lot easier. Just if I put it in slope-intercept form, there's a good chance, based on the experience with the last problem like this, that the y-intercept will probably be something nice. All right, so our function is this secant x plus 1 plus 2 root 3 pi over 3 at x equals -pi over 3. So here's the function we're given. Secant of x plus 1, then plus 2 times the square root of 3 divided by 3, times pi. And then at the point where x equals negative, pi over 3 or 60 degrees, -60 degrees, if you remember degrees, but we're going to stick to radians, right? So again, we want our tangent line. Right? So again, the point on the line, -pi over 3 for the x coordinate, and then f of, plug it in, -pi over 3. So that's the secant of -pi over 3. And then, plus 1 plus 2 root 3 over 3 times pi. Right, so this here, so you might recall the cosine of 60 degrees or pi over 3 radians was a half. same thing for negative pi over 3, was a half. So this is the reciprocal of that. So this is just 2, all right, and then plus 1 plus 2 root 3 over 3 times pi. All right, so we got 3, all right, 2 plus 1, plus this 2 root 3 over 3 times pi. So there's my y coordinate of the point that we're at. And if you want to go to Desmos like I was doing earlier and check that, you can, but I'm done with that. All right, let's get this over with. So, point, now I want the slope. So again, f prime at x. The derivative of secant of x was the secant of x times the tangent of x. And then the rest of it's constant. All right, there is no x in the rest of it, so the derivative of the rest of it, the other terms, are 0. So this is it. So then at negative pi over 3, and we got the secant of negative pi over 3, which we just saw was 2, and then times the tangent of negative pi over 3. Secant of negative pi over 3, again, that's 2. Now the tangent, remember the sine of negative pi over 3 would be negative, root 3 over 2. Cosine is half. Divide sine by cosine. Dividing by a half is multiplying by 2. That's negative square root of 3, this tangent of negative 60 degrees or negative pi over 3. So our slope is negative 2 root 3, or 2 times the square root of 3. Putting all this together, the equation of our line. So we got y, I'll put it in point slope form first, and then we'll go to slope-intercept form, and it'll hopefully make moving that other point on the graph they have for us a lot easier. So y minus the y coordinate of my point, which was this 3 plus, 2 root 3 over 3 times pi. Equals, and then the slope, this negative 2 root 3 times the quantity, and then x minus the x coordinate of my point. So x minus negative pi over 3, that'd be x plus pi over 3. Okay. So if I put this in slope-intercept form, look, distribute this. Negative 2 root 3. So I'll have negative 2 root 3 times x, and x is not in the root. Slope times x, and then now minus 2 root 3 over 3 times pi. So you see when I add this quantity here, this 3 plus 2 root 3 over 3 times pi, when I add that to get y alone, adding this to both sides, see that 2 root 3 over 3 times pi goes away. And I'm left with this y on the left equals, my slope, negative 2 root 3 times x, mx plus b plus 3. All right, so that's key right there. The y-intercept is 0, 3, and that's where I'll move this other point. So you see they have the point there already on the graph where x is negative pi over 3. You're just moving this other one to the y-intercept there, and look at that. That's definitely tangent to the curve at that point. Pointing in the direction at the curve at that of the curve at that moment. So 0, 3 would be the other point I'd like to plot there. Great. So looks like another one of these. All right. All right, I'll write it out. It's again, doing these in my head, probably not the best idea. All right, so write it out again. So the function we're given here is another secant one. This time you got 2 times the secant of x minus 6. And then you have this plus 4 times the square root of 3 over 3 times pi, right? There's pi in the numerator there. At the point where x equals pi over 3. And once again, they already have this point where x equals pi over 3 plotted for you, right? You just have to move some other point to make the tangent line. So again, to write the equation of the tangent line, the point as this x coordinate, right, pi over 3, and then the y coordinate. Now, I've already mentioned the secant of pi over 3 is 2. So this is 2 times 2, this is 4. 4 minus 6 is negative 2. So we have negative 2 plus this 4 root 3 over 3 times pi for the y coordinate. Or you could write 4 root 3 over 3 pi, 3 times pi, and then minus 2 for after, but you know that's the y coordinate. And then the slope and f prime. This is going to be 2 times secant tangent, right? The derivative of secant was this secant times tangent. And then the rest of this is constant, right? These don't have x in it, right? So these terms, derivatives is 0. And then at, pi over 3, for this particular x value, you got 2 times, the secant of pi over 3 I already said was 2. And the tangent of pi over 3 is the positive square root of 3, right? This is positive 60 degrees positive. So that's positive square root of 3 as opposed to negative square root of 3 like it was in the last problem. So we end up with 4 times the square root of 3 for the slope. And so we have y. So our line, I'll do point slope form again. Y minus the y coordinate, this negative 2 plus 4 root 3 over 3 times pi, should be equal to the slope, 4 root 3, times the quantity x minus pi over 3. All right, just x minus the x coordinate. After distributing this 4 root 3 over here, we end up with 4 root 3 times x, slope times x, then minus 4 root 3 over 3 times pi. And you're going to see that, when I add this over here, we're going to have that negative 2 over here and plus 4 root 3 over 3 times pi over here. These 4 root 3 over 3 times pi's will go away, and I have minus 2 left over. We got y equals 4 root 3 times x, slope times x, and then minus 2. There's your y-intercept. 0, negative 2 is where I'm moving this point. And when I do that, right, so 0, negative 2 is down here. You see when I move that point to 0, negative 2, definitely a line that is tangent to the curve at this point where x equals pi over 3, right, goes in the direction the curve is going in there very nicely. Great. And that's it. All right, so again, hopefully watching me go through all these here help you in some way when you're working on the assignment yourself. And thank you very much for watching.